All right, hello everybody. This is a video for my wonderful colleague, Miss Moose, about expected value. So please ask questions, or if you need more examples, let me know. I'm happy to do it. So the idea of expected value makes sense when you think about doing something over and over and over again. If there's some randomness involved, what do you expect to happen on average over the long run? So let's look at a game. So let's look at a game of flipping a coin. And if we're flipping a coin, let's pretend it's fair. And let's say that if it is heads, then you'll get $2. And if it is tails, you have to pay $1. So this is a pretty sweet deal for you. If heads, win $2. If tails, lose $1. So what happens depends on probability, depends on randomness. So one possible way that this game could go is we could go heads, heads, and tails. And what would be the total outcome after that? Well, if I played it 3 times, then I would get $2 plus two more dollars, and then I lose $1 for the tails at the end. That means that I'm up $3. It's also possible that I went tails, 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 and that would be losing a dollar, losing a dollar, losing a dollar. That would be a bad outcome. It's also possible that I had heads, heads, and heads. That'd be winning $2 and $2 and $2. And so that'd be winning a total of $6. And so it turns out that there are a lot of different possible outcomes for playing this sort of a game. And what we want to look at is what would you expect to happen over time if you played the game over and over and over again. Okay? And so the way that you figure out your expected value of x here is equal to the way the formula looks can be just a little bit intimidating. The formula, sometimes they'll use the letter mu here. Those mean the same thing. It's the sum over all of your possible outcomes of x times the probability that x is equal to x, like that. So this right here is saying you multiply the outcome multiplied by the probability of that outcome. Okay? And so if we look at expected value of a certain game, what we want to know is what are all the possible outcomes and what are the probabilities of those outcomes. So let's look at our example here of flipping a coin. If I take those, like I showed you, if I played the game 3 times, there's lots of different outcomes that could happen. And what the expected value tells you is what would you expect to happen on average if you played the game a lot of times. So let's use our definition right here. The expected value of our coin flipping game is equal to the sum, so I'm going to be adding up all of these possibilities, of an outcome, so $2 times the probability of that outcome, heads, happens 1/2 of the time, plus the other outcome, lose a dollar, times the probability of that outcome, tails, 1/2. Here it's a little simple because there's only 2 possible outcomes, and so I only have to do 2 calculations. 2 times a half, -1 times a half is a half. So you get 1/2, or if we want to think about it, you can think about it as 50 cents. So what this tells you is that in the long run, expect to earn 50 cents, 0.50 per game. Now I want you to notice something that can be confusing about expected value. This is one of those situations where the math language might not match with what you'd expect it to mean. The expected value is not one of the outcomes that's possible. The only two outcomes that are possible here are you either win $2 or you lose $1. The expected value, though, is a positive 50 cents. And what that is saying is that if you played the game 100 times, you would expect to earn 50 cents each of those times. So it is very likely that if you played it 100 times, you would earn $50. That your all of those possibilities that I was showing you, like you could have made $6, you could have lost $3, you could have made $1, that on average, those settle down to give you a nice symmetrical distribution. And right in the middle of that symmetrical distribution, your mu is your expected value. Okay? So the idea is that in the long run, the expected value tells you the average outcome of the game. And you can think of it as creating one of those nice symmetrical distributions where the highest peak is right there at mu. In other words, is right there at the expected value, 50 cents per game. So if I played it 1,000 times, I'd expect to be up about $500 on average. I'm not saying that it's a guarantee. It's just saying that's the most likely outcome, and it gets less likely the further you get away from the expected value. Like if I played 1,000 times, it would be almost inconceivable that I would lose $1,000. Let me draw the little picture. If we think about playing the game 1,000 times, the 500, which is 50 cents times 1,000, will be right there in the middle. It'd be almost inconceivable to lose $1,000, and it would be just as inconceivable to gain $2,000. Okay, so that's kind of the image in your head. It doesn't need to be perfectly symmetrical, but the idea is that the expected value is right there in the middle. Let's look at another example of expected value, because sometimes they'll just give you some random distribution and ask you to calculate expected value for it. So let's say, from as just an example, the probability that something happens is given by this. And the only b values are 0, 1, 2, or 3. So if I want to find the expected value, first I got to figure out what the heck's going on with this k value. And so what I know is that if you add up all the probabilities, you have to get 100%. So I know that if I do k times 4 minus 0 plus k times 4 minus 1 plus k times 4 minus 2 plus k times 4 minus 3, all of that has to equal 100%. So it's got to equal the whole number 1. So in other words, 4k plus 3k plus 2k plus k equals 1. So I think that's 10k. So k is 1/10. Or if you like decimals, you can write 0.1. So the expected value here would be adding up each of my outcomes times the probability of that outcome. Okay? So the way that's going to work here is I'm going to take my b value of 0 and I'm going to multiply it by the probability that I get 0 using my probability function right here and using my 0.1 that I just solved for. So 0 times k times 4 minus 0. Then I look at the next one, probability of 1 times k times the probability of 1 plus b equals 2. Notice I'm using the same exact k value every time. And then I have b equals 3 as my last one. Okay, so in each of those steps, what I just did was I did b times probability of b. Okay, so this was 0 times probability of 0, plus 1 times probability of 1, plus 2 times probability of 2, plus 3 times probability of 3. So each of those was just following our expected value formula. So calculating that, I really encourage you to use a calculator as you go through it. If you're stubborn and you want to do it by hand, you can see that this is going to equal 0. This is going to be 0.1 times 3. So we'll have 0.3. This is going to be 0.2 times 2. So you'll have 0.4. This is going to be 0.3 times 1. And 0.3 plus 0.4 plus 0.3 is equal to 1. So what does this mean? This doesn't mean that you're guaranteed to get a 1 out as an answer. This just means if you played the game a lot of times, if you repeated this experiment a lot of times, on average, you would expect to get a 1 as your result. Okay? So that's kind of the idea of expected value. Please like, either comment if you have any questions, or let me know if there are any other examples you'd like me to do. There you go.